So, where did we stop yesterday?
The topic is on the board.
Oh yes, thank you. Let's start. As we know, any type of treatment facility contains not only nitrifying and denitrifying bacteria, but also many other types of bacteria, whose life activity is no less important for wastewater treatment. Thus, we, as wastewater treatment specialists,
We have to create the favorable conditions for growth of microbial communities which decompose pollutants and neutralize pathogens. I'm sorry for interrupting.
That's okay, Betsy. Now let's take a closer look at the exact methods that allow us to select those microbial groups that treat various types of wastewater. There are 4 selection methods. The first method. Let's imagine that these 2 rectangles represent 2 states of a wetland. This wetland doesn't contain substrate, while this one does. The substrate allows the biomass of the attached microbial community to increase many times per unit volume of the wetland. The second method. As we know, every wetland has aerobic and anaerobic zones. Moreover, in certain conditions, each of the zones can change into its opposite, aerobic to anaerobic and vice versa. The interaction of aerobic and anaerobic zones, both in space and time, results in productive biomass growth of both bacterial groups and creates a bacterial community that treats wastewater more efficiently. The third method deals with the delivery of substrate to a particular wetland zone, where the bacteriocynosis is specific to the recycling of a given substrate. Betsy, what is the source of primary substrate?
Wastewaters flowing into the wetland.
The third method of bacteriocynosis selection is redistribution of secondary substrate. It can be performed in 2 ways, either by recycling of secondary substrate or by the redistribution of the substrate into sections specially designed for its processing. And finally, the fourth method is based on wastewater heat conservation. Betsy, what are the ways to conserve heat?
There are 2 ways. The first one is to construct a wetland in the closest vicinity to the wastewater source. The second is to insulate the wastewater pipes and wetland walls.
And thus, by conserving the heat of the wastewaters, we increase metabolic rate of bacteria, which treat the water. The discussed methods of bacteriocynosis selection allow us to construct and exploit wetlands regardless of climatic zones and the biochemical composition of wastewater. Ms. Doolittle, do you have any questions?
Only one. How to relate all of this to hydraulics?
It's easy. Come out to the board. Remember, hydraulics don't age. Betsy, the thing is that without laws of hydraulics, these methods just won't work. To successfully apply these methods, it's necessary to accurately calculate water velocity and its retention time on each side of constructed wetland, each of which has its own structural features. Now tell me, what is the basis of constructed wetland hydraulics?
The calculation of a water balance.
Good. Please write on the board, water balance. Moreover, we should definitely take into account that any type of constructed wetland is part of the landscape. Any landscape incorporates atmospheric precipitation and storm runoff. In addition, constructed wetlands are a part of the landscape and, as a treatment facility, also have to incorporate wastewater that's to be treated. Because of this, a wetland's hydraulic load consists of 3 components: atmospheric precipitation, storm runoff, and wastewaters that transport biowaste generated by humans. The water balance of a wetland as any body of water is based on the equilibrium between the total water input and total water discharge. Discharge is referred to evapotranspiration from a wetland surface, water overflowing a wetland's perimeter, for example during a rainy period, and the most important, treated effluents. Thus, the water balance, as well as the homeostasis in the bodies of living organisms, supports the stability within a wetland, so that it doesn't dry up or that the water doesn't overflow the borders of wetlands construction, no matter what the weather is. Does that make sense, Ms. Doolittle?
Yes, Professor.
Then, I'd like you to answer some questions. The first question. Let's take, for example, a horizontal subsurface flow constructed wetland. What is technically specific about how wastewater enters this wetland? I'll give you a hint. It's directly related to the laws of hydraulics. And the second question. What mechanical device installed at the outlet of any constructed wetland regulates wetland water level? This device maintains water balance according to the laws of hydraulics.
Can I take some time to think about it?
Of course you can.
I'm ready to answer, Professor. As for the first question, wastewater entering the wetland is split into several flows. In this way, a stable flow of water is ensured, which allows the most efficient use of the volume of the whole wetland. As for the second question, wetland water level is regulated by a simple mechanism that is called a gate valve, as far as I remember, sir.
Correct, Betsy. You have good memory. Now it's about time to move on to Darcy's law. Firstly, could you tell me what this law says? And secondly, could you explain why we need it?
If you don't mind, sir, I'll start to the second question.
Go ahead.
When building a subsurface flow constructed wetland, it's important to consider that sometimes influents pass above a wetland's working surface and thus remain untreated. To prevent this problem, it's necessary to apply Darcy's law when calculating a wetland size. Darcy's law is the main law of hydraulics, which describes the water filtration process through substrate. In other words, Darcy's law is characterized by a functional relationship between the water filtration rate on the one hand and the product of three values on the other hand: hydraulic conductivity, the cross-sectional area of the constructed wetland, and the hydraulic gradient. Technical engineers would not be able to design a wetland without Darcy's law.
Exactly. Moreover, Darcy's law is a fundamental part of each method of selection of microbial communities.
Taking that into account, Professor, you probably have a question for me.
No, Miss Doolittle, it's not a question, it's a problem. Please, write the following on the board. The water flow rate of the constructed wetland is 40 cubic meters per day. The hydraulic gradient is 0.01. The hydraulic conductivity of gravel is 80 meters per day. I'd like you to calculate the cross-sectional area of the constructed wetland. Am I going too fast?
No, but please give me 2 minutes to calculate.
I have the answer, Professor. The cross-sectional area of a wetland is 50 square meters.
Wonderful. I think now we have more or less the hang of hydraulics. As I remember, our next topic is...
The removal of phosphorus and metals from wastewater, sir.
Oh yes, thank you. But before we move on to our next topic, we should discuss some basic things.
Of course, Professor.
We have to review the solubility of phosphorus and metal compounds in organic environment. It's essential to understand how these chemical reactions are interconnected with biochemical processes taking place in constructed wetland. But let's discuss it tomorrow.
But maybe today at least we could start.
I'm afraid I can't. I'm late to the theater. They're putting on a new interpretation of Bernard Shaw's Pygmalion.
I know that play, Professor.